Chapter 7 is titled Analytic Trigonometry. In the 7.0 preview, we're going to look at what are called fundamental trig identities. These identities will be useful for simplifying and solving equations. You'll be given these identities on your assessments, but you'll need to know how to incorporate them. We have reciprocal identities, where we talk about the definitions just in fraction form. For example, cosecant of theta is the same as 1 over sine theta. We used that identity when we were trying to evaluate with a calculator. Sine would then be the same as 1 over cosecant, and so on. We have secant and cosine, cotangent and tangent. Pythagorean identities relate the sides of a triangle in terms of trig functions, and we have 3 of them. Sine squared plus cosine squared equals 1 plus tangent squared theta equals secant squared, and 1 plus cotangent squared equals cosecant squared. The quotient identities are fairly common. Sorry, we've got Pythagorean identities and quotient identities. We'll use these two quite a bit, as not only are tangent and cotangent related to each other, but notice we can also write them in terms of sine and cosine. And that's what we did when we evaluated the unit circle. Sine and cosine would be y over x, and then cosine over sine would have been x over y. Even odd identities just have a negative with the theta value or your angle, which would indicate a clockwise measure. Now, depending on which trig function you're dealing with, sometimes that negative rotation doesn't impact your sine, cosine, or tangent values, and sometimes it does. And that's all even odd identities do. Sometimes they bring that negative from the theta out in front of the trig term. Cofunction relationships just deal with values that are complementary, or they would add up to pi over 2. Cofunction is where sine and cosine match, tangent and cotangent match, and secant and cosecant match. So these are the cofunction relationships. We'll use these values down below. As I mentioned earlier, these fundamental trig identities are going to be useful when we simplify expressions. And they're also going to be useful when we solve equations. Some things to note: when you have something like 1 minus cosine squared, that's kind of a spin-off of this Pythagorean identity up here. 1 minus cosine squared means you're moving cosine to the other side by subtracting. That's what moves it over. That would equal sine squared theta. So just taking that Pythagorean identity and rewriting it. But notice it won't be the same if you square root each side. So I'm just going to kind of get rid of that up here. So if you just have 1 minus cosine theta, that doesn't equal sine theta. We can't just square root that Pythagorean identity. But let's use kind of just different ways to interpret that and rewrite that identity 3 different ways. Well, we've already done one. If you move cosine squared to the other side, you could rewrite the identity simply by saying sine squared theta equals 1 minus cosine squared theta. That's just a different interpretation of that Pythagorean identity. Think of another way to write that. What if we kept cosine on the left and moved sine to the other side? That means cosine squared theta would be equivalent to 1 minus sine squared theta. Can we think of another way to rewrite this? What if I moved 1 to the other side and either sine or cosine to the right-hand side? That would give us something like, I don't know, maybe sine squared theta minus 1. So if I have 1 on that left-hand side, that means I have to move cosine over to the right, which would make that negative cosine squared theta. Just some ways to interpret those Pythagorean identities. Let's try other ways to use the identities to help fill in the blank. What we're going to do is have an answer that's either going to be simply a number or just one trig term. We have sine theta times cosecant theta. Well, looking up above, notice right away in that reciprocal identities section, sine and cosecant are reciprocals of each other. Because of this, we can take one of those two terms and apply that definition. And I'm going to use cosecant. If I keep sine theta as is, and I rewrite cosecant theta as 1 over sine theta, then technically sine over 1 times 1 over sine cancels out. And we have 1 divided by 1, which is just 1 left over. So anytime you multiply a term by its reciprocal, they cancel out to equal 1. In the next one, cotangent squared A equals cosecant squared A minus blank. Well, anytime you see something being squared, that's likely one of the Pythagorean identities. Now I notice 1 plus cotangent squared equals cosecant squared. So if I have cotangent squared A by itself on that left-hand side, that must mean we moved 1 over to the right. And you'd have to move that 1 over by subtracting. That means this is equivalent to cosecant squared theta minus 1. Just taking that Pythagorean identity and moving one of the terms around. Cotangent B times sine B. Well, if I look at the reciprocal identities, cotangent and sine aren't reciprocals of each other. So that one's not really going to be helpful. This is going to be an example where the quotient identity is going to help us simplify to one term. If you see cotangent B, that definition is the same as cosine divided by sine. So if it's cotangent B, that's going to be equal to cosine B over sine B, keeping that angle the same variable. And if we multiply that by sine B over 1, the signs cancel out. Look at that. And all we have left is cosine. So just using that quotient identity to help us here. You try the next one. Secant squared theta minus 1. Where do you see a definition or an identity up above that has both of those terms in it? And can you tell how we got this kind of connection with that identity? If we move 1 to the other side to be secant squared minus 1, all that's left in that Pythagorean identity is tangent squared theta. There's our one trig term and our final answer. Letter E. We'll just go through as many of these examples as we can. Sine R divided by cosine R. Well, if I look at all of my identities up above, there's a definition that has sine divided by cosine, and that's the quotient identity for tangent. So sine R divided by cosine R equals tan of R. Just using that definition for the quotient identity. Sine negative theta times cotangent theta. Let's try this one. Sine negative theta, that's an even odd identity. If there's a negative with your theta, that just equals negative sine theta for the output. Now cotangent theta, we have a couple of cotangent options for our identities, but the only one that works with sine is again that quotient identity. So very similar to example C up above. Cotangent theta would be the same as cosine theta over sine theta. Now, when we simplify this and we put sine theta over 1, the signs cancel. And this time we have a negative times cosine. That makes our answer negative cosine theta. How are we doing so far? Just kind of applying those identities up above. All right, watch what happens here. Secant squared A minus tan squared A. Well, anytime we see something being squared, that should bring your eye to the Pythagorean identities. If I have secant squared and tangent squared on the same side, that means I move tangent over by subtracting. The only thing that's left on that left-hand side then for the Pythagorean identities is 1. But watch what happens if I flip the order. Tangent squared A minus secant squared A. If I move secant to the left with tangent, that means we have to move the 1 to the right. And if we move 1 over to the right, we have to do that by subtracting, which makes tan squared A minus secant squared A equal to negative 1. And these are just some examples on how to use the fundamental trig identities to simplify specific statements. The rest of the 7.0 refresher lesson is just review. We're going to do a little bit of review from Chapter 6a, and then a little factoring review from either functions class or Algebra 2. When evaluating a function, the first step is sketching the triangle in the appropriate quadrant. Now we did work with this back in chapter 6a. We're going to do the same kind of work in chapter 7. So I brought back this chart over here on the right. Remember in quadrant 1, all 6 trig terms are positive. But in quadrant 2, only sine and cosecant are positive. The other 4 are negative. In quadrant 3, tangent is the only one with cotangent that are positive, but cosecant, sine, cosine, and secant are all negative. And then last but not least, in quadrant 4, the only pair that hasn't been positive other than quadrant 1 is cosine and secant. They're positive also in quadrant 4. The other 4 are negative. It says given secant u is negative 3 over 2 and tangent u is greater than 0, determine the values of the other 5 trig functions. So now instead of theta, we're using the letter u as our angle measure. If secant is equal to negative 3 over 2, secant u, that's the definition hypotenuse over adjacent. Secant is the reciprocal of cosine. And cosine is negative in quadrants 2 and 3. Now it says tangent is greater than 0, which means tangent is positive. And tangent is positive in quadrants 1 and 3. That's going to help us determine where we draw our picture. The 2 values are the same in quadrant 3. That's when secant is negative and tangent's positive at the same time. So if you recall, that's what helps us create our triangle down in quadrant 3. So I'm just going to draw my terminal side somewhere in quadrant 3, connect the triangle with the x-axis. Now we have to be careful here. This angle is u, it's not theta anymore. And if the hypotenuse over adjacent is negative 3 over 2, only one of those values can be negative. Now remember, the hypotenuse is always positive. That would mean when we count to the left on the x-axis, the x-coordinate is negative. To find the other 5 trig functions, we do have to do Pythagorean theorem to get that missing side length. If you do a squared plus b squared equals c squared, we would get negative 2 squared plus b squared equals 3 squared. Negative 2 squared is positive 4, and 3 squared is 9. Moving 4 over, we would get b squared equals 5. And to get b by itself, we'd have to take the square root. If I put 5 over on that left-hand side, we're counting down on the y-axis. So if I put square root 5 over here, we have to also recognize that it's negative, because direction will matter as we list out our trig functions. All right, just as a little review, please pause the video and see if you can determine the other 5 trig functions of angle u. Press play when you're done, and then we'll work on some factoring. Okay, how did you do? If we have that y value being negative square root 5, sine u just equals opposite over hypotenuse, or negative square root 5 over 3. Cosine u is just the reciprocal for secant, that's just negative 2 over 3. Tangent u, check this out everybody, did you notice that tangent and cotangent are positive? That's because the x and the y value will cancel the negatives out in the fraction. Tangent of u equals square root 5 over 2. Now cosecant is the reciprocal of sine, but we had to rationalize the denominator. That gave me negative 3 square root 5 over 5. And then finally cotangent u, 2 square root 5 over 5. If you have any questions on how those fractions came to be, make sure to ask. Also remember to include that angle u with each of these definitions on the left-hand side. I'm going to finish the video with a little bit of factoring review. We will end up factoring with trig functions. This gets kind of crazy very soon. I wanted to just give you a refresher on factoring like we did in Algebra 2 and functions, just as a preview when we include trig terms. Often when factoring, you want to check for a common factor first. And a common factor is just something that you can divide out of all the terms in your polynomial. If we have something like 4x minus 12, both of these terms have a factor of 4 in common. If I put that to the outside and create a product, we can have a smaller set of values inside that parentheses. Factoring 4 out of 4x would give us x left over, and then we keep the same sign. If we factor 4 out of 12, 4 goes into 12 3 times, we'd have x minus 3 left over on the inside. So factoring is just a way to break down a polynomial into a product of smaller parts. In the second one, x squared plus 5x, this time each term has an x in common. That means we can take that out as the common factor. If we take x out of x squared, we just have x left over. And if we take x out of 5x, we have 5 left over. And there's another example of a common factor. Now watch this last one. We have 5x squared plus 15x minus 35. It's pretty easy to see that all the terms have a 5 in common. And when we take that out, we would have x squared plus 3x minus 7 left over. And that won't break down any further. So sometimes when you have a common factor, you still have a quadratic expression in the parenthesis that doesn't break down further. Now in the next section, it says if you have a quadratic expression of the form x squared plus bx plus c, the thing to note about this one is that the number in front of x squared equals 1. So a would equal 1. You may need to split the constant, that c value, to get the b in the middle. So it says factor x squared minus 9x plus 20. The 20 is the c value, that constant. We want to figure out all the possible ways to multiply numbers to get 20. We could do 1 times 20, 2 times 10, or even, well, there's a 10 there, or even 4 times 5. Now, is there a pair that would some way work to get negative 9 when we add them? If we make the 4 and the negative, or the 5 negative, that would give us positive 20 when we multiply and negative 9 when we add. That means this will factor into a product of 2 smaller parentheses. X squared splits up into x times x, and then minus 4 and minus 5, and you could write those in either order. So that product would give you x squared minus 9x plus 20 when you multiply. Now in the problem on the right, it seems a little unique because there's that 2 out in front. But if you notice, all 3 coefficients are even numbers. That means 2 is a common factor. We would want to take that 2 out if possible. And that gives you x squared plus 7x plus 12. And now that number out in front is just a 1, so I can take the c value and try to split it. Numbers that go into 12 include 1 times 12, 2 times 6, and 3 times 4. Now in this set of factors, the 3 and the 4 would also add to get 7 in the middle. That means we can split this polynomial into a product of smaller parts. The x squared splits into x times x, and then we'd have plus 3 and plus 4 in either order. And last but not least, everybody, don't forget to put that 2 out in front as the common factor. And I think this is going to be a good stopping point. We'll finish the rest of the problems tomorrow in class.